So we'll record it for this class here. All right, so today, chapter 9, we are now, instead of doing confidence intervals, in fact, we actually can use confidence intervals a little bit for this process. But what we're going to be focusing on in chapter 9 is doing what we call significance tests, or tests of significance. Basically, we're going to collect samples, or a sample statistic, and use it to compare to something we think is the actual parameter. So when we do a significance test, as it says right up here definition-wise, you're going to take some observed data. You're going to compare it, okay, to some sort of claim. This claim we'll call a hypothesis that we want to assess some truth about. So we believe something to be true. So we're going to collect a sample and see, hey, does that sample seem to support that truth? Or does it seem to say, something's wrong? So this claim that we will focus about will always be about a parameter. Specifically in this class, we will talk about it being a population proportion or population mean. So you'll see us use P and mu all the time when writing these hypotheses. So just to give you an idea of what these hypotheses might start to look like, or what we might be talking about. A claim might be something like this. A basketball player makes 80% of all her free throws. Okay? You'll hear that on the news, I should say on the news when you watch a basketball game. This player makes 70% of all their free throws. Okay? Well, that's a claim. Okay. Likewise, the mean ACT composite scores of Hopkins High School students is 22.9. Okay? That's the average. Yep, that's the population mean. Okay? So, when we do a significance test, we write two hypotheses, okay? And this is a little bit, for some, kind of a little bit of backwards thinking with statistics, okay? We start off by writing what we call a null hypothesis. When you think about the word null, I want you to think about the word 0. Notice how the symbol here is H sub 0. It's known as the null hypothesis. Okay? It's basically a statement of the claim we want to compare. I think of it as the claim of what we expect, that nothing, or 0, nothing, is out of the ordinary. Think about this. We might have a coin in front of us, and we're going to flip that coin 100 times. We assume a coin is a fair coin, meaning we'll get the same number of heads and tails. So what we could do is we could actually say, all right, my null hypothesis might say the probability of getting heads is 0.5, or getting tails. Now the alternative, alternative A, H sub A, that's the symbol for alternative, is a statement or claim we hope or suspect to be true instead of the null hypothesis. So we might suspect, hey, this coin might not be a fair coin. So if we don't think it's a fair coin, well, then we could say the proportion doesn't equal 0.5. The true population proportion of heads might be 0.55. It might be 0.45. We don't know which direction, hence why we're doing a not equals to. Now, what happens here is when we write these null and alternative hypotheses, we'll talk about it being one-sided or two-sided. When we talk about it being one-sided, what happens is this alternative hypothesis, this h of a, we'll talk about it being either greater than some number or less than some number. So if the problem specifically talked about with the coin tossing, said, we're getting a higher proportion of heads, we would say greater than. If it said we get a smaller proportion, we suspect that it's a smaller proportion, we'd say less than. So there'll be problems where we'll suspect it to be higher or lower, greater than or less than. Other times, we won't know what the actual proportion is. So when we don't know what it is, it's two-sided, meaning we don't know if it's higher or lower. So we'll use this not equals. So like in a coin toss, if we don't suspect it one direction or other, we'll say not equals, because if we get events or too many heads, we'd suspect that it's unfair. Or if we don't get enough heads, we would suspect that coin to be unfair. So one of the things in a test of significance problem that you need to become comfortable with is writing these null and alternative hypotheses. Writing these null and alternative hypotheses using the symbols and what the symbol represents is in essence your step one, going back to when we were doing confidence intervals. Instead of saying we're going to find a 90% confidence interval, what we're going to say is here's our null hypothesis, here's our alternative hypothesis, and here's what my variable represents. Think of this almost kind of like a science lab. So, to get us started here, first example. Whoops, I don't want to give it away here. It says, each problem calls for a significance test. State the appropriate null hypothesis, alternative hypothesis. Be sure to define your parameter in each case. So, study on teenagers and their behavior revealed that 72% of all teens said they seldom or never argue with their friends. Jovan wonders whether this national result would be true in her large high school. So she surveys a random sample of 150 students at her school. So in her case, when we talk about the null and alternative hypothesis, the null hypothesis is, in essence, her school is just like the national average. Nothing out of the ordinary is different from her school compared to what the national average is. So we would say the population proportion of her school is the same as the national average, 0.72. The alternative is, well, she wants to know, is her school different than the national average? It didn't say, is her school have a higher percentage or a lower percentage? She's just wondering if it's the same. So since we don't know it's higher or lower, it needs to be a not equal to, because we don't know which direction it's going if it's different. So our alternative P is not equal to 0.72. Then you always need to make sure you tell me what the symbol you're using represents. In our case, it's the population proportion of students at Jovan's school who rarely or never argue with their friends. I'm guessing a few of you have been arguing with your friends about the Viking football loss. And whose fault it is.
AP's fault.
It
really is. Adrian Peterson.
It's a curse of something. That's all I gotta say.
They cheated.
They cheated.
They played the ball. Just like A 2.0.
Alright. See, I'm going to give you a minute head start and see if you can try to do number 2. Just to let you know, again, symbol notation is important. Make sure you're using the correct symbol. So I'll give you a quick minute to try number 2. Alright, again, let's take a look at this one here. This one is tricky at first because many of you like to think, oh, we did a proportion on the last one. This one must be a proportion, and it's actually not a proportion. It doesn't talk about a percentage here. It is actually talking about, hemoglobin levels. And it says here, people with less than 12 grams of hemoglobin per deciliter of blood are considered anemic. So we're wondering, do we have evidence to basically claim that? That actually goes into our alternative because we're trying to show evidence that this might be happening. Okay? The assumption is that they aren't. So if they're not, the mean would equal 12. Now I know some of you would say, well, couldn't it be greater than 12 and you'd still be okay? Yes, true, but for tests of significance, we always have the null hypothesis be equal to. The alternative will be your less than, greater than, or not equal to. So the mean again is the true mean amount of hemoglobin in Jordanian children. Nicole. Yeah. The null hypothesis is making the assumption that nothing is wrong. So if the hemoglobin level is at 12, they don't have anemia, right? So we assume nothing's wrong. The alternative is we're going to try to show evidence. Yeah. So now if we collect a sample and get a result that says, we need to, in essence, later on I'm going to talk about this, reject this, we'll show evidence that this might be true. Yeah. Okay. All right, so now, are we okay with this example? All right, so now, how do we go about showing, whether or not, or let me rephrase it this way, how do we conclude one of these hypotheses, or hypotheses? Okay? Do we, reject our null hypothesis and say, the alternative seems to be right, or do we think our alternative is A-okay? Okay? So now, in essence, when you think about a null hypothesis many times, we're going to basically look at collecting evidence against it. We're trying to see, boy, does our sample tell us that the null hypothesis is not true? This is kind of a different way of thinking. In statistics, we don't prove things to be true. We show, or we look at a statistic and say, does this give us evidence that something's wrong? Or something just seems highly unlikely so that we should be concluding something else. So how we go about doing that is we calculate and interpret what's called a p-value. What I like to think about a p-value is, you can see how I have here written in blue, and I'll draw another picture of this too here in just a second, but I think of the p-value as a conditional probability. Okay? It's the probability that your sample that you collect, either your p-hat or your x-bar, occurs, okay, given that your null hypothesis is true. So this is the assumption you are making. You are going to make the assumption that everything's A-okay with the null hypothesis. So for instance, if I'm thinking about flipping a coin, and I go back to the coin example, the null hypothesis assumes that the probability of my sample getting heads in my sample will be 0.5. So my p-hat becomes my mean here at 0.5. So what will happen is, I might flip a coin 100 times, and I might get a result of, say, 55 heads. Is that enough of a result to say that the coin is not fair?
Yeah.
I don't know. So what happens is I take my sample result. So somewhere over here will be my sample result. And now I'm using p hat again of 0.55, and I'm going to calculate out this probability. This probability is what you call your p-value. It's the probability of your sample result occurring, making the assumption that the null hypothesis is true. That the population proportion, and really this should be p hat, this should just say p, is 0.5. So ideally, if you're trying to show statistical evidence that something's wrong, the smaller your p-value needs to be. Okay? Because, say if this was 15%, 0.15, it'd be like saying, well, 15% of the time I would get a result like that. Well, 15% is like 1 in 7, 1 in 6 times. Okay, I know that's not every single time, but that's not a very low probability. Okay, so, if we get large p-values, those fail to give us convincing evidence against the null hypothesis. So like the example I was talking about, 0.15, probably is not enough to say that the null hypothesis is false. Okay? So the question is, how do we go about drawing our conclusion? First of all, what are the two conclusions that you will make? You are going to make one of two conclusions. You are either going to reject the null hypothesis or fail to reject it. We never actually prove the null hypothesis true. Okay? We just either have statistical evidence to say it's false, or we have statistical evidence to say, you know what, we got a result based on what we would expect to get. Okay? Now the question becomes, what p-values make it so that you reject it or fail to reject? Technically, there isn't a specific value. There is no set value that guarantees that you reject or not reject. However, we statisticians love to make up our rules. So what happens is sometimes in problems, you're going to get what's called a significance level. And we use the Greek letter alpha, another Greek letter to throw into your Greek alphabet. Many times, it will be given to you. However, if it's not given, we use 5%. So, if our p-value is less than 0.05, that's our line in the sand. That is the line where we decide, do we reject or do we fail to reject? Okay. So, what happens is this. If the p-value is less than alpha, so if it's 5% or 1% or whatever percentage it is, if it is smaller, okay, we reject the null hypothesis and we can conclude the alternative is true. So for instance, if I flip my coin 100 times and I calculate out my p-value and it ends up being 0.02, 2% of the time my result would occur, or something like that even farther away would occur, I would reject my null hypothesis saying, you know what, I have statistical evidence that my coin's unfair. However, if that p-value is greater than or equal to alpha, so if it's bigger, we fail to reject the null hypothesis. Also notice how we can't conclude the alternative is true. We would basically say, hey, you know what? We got a result that we would expect from time to time. Or sometimes we'll say our result is due to what we call a chance variation. You know, yes, it wasn't the exact mean, but we realize variability occurs, and it was close enough to the mean to account for that variability. So on the next page, it's going to be important to be able to interpret what the p-value means, okay? And then based on that p-value, make the correct judgment. So what we're basically going to be doing on the next page is our step 4. Okay? So the null and alternative hypothesis is kind of like our step 1. This next part is like our step 4. So, next page. I'm going to cover it up here. Oops, I don't know why that's still there. So, in number 1 here, it says, in the previous example, for Yovan's survey, 96 students in the sample said they rarely or never argue with friends. Okay? A significance test yields a p-value of 0.029. I'm sorry, it's 0.092 or no, 0.0291. My goodness, what am I? I'm just making up numbers right now. Sorry about that. But here's our p-value. So if it helps you to visualize what's going on here, it's this. Since Yovan's is a two-sided test, since it's a not equals to, her p-value, a result like hers or one more extreme, is going to be located this far away from the mean, such that the p-value, the area under the curve here, equals 0.0291. So, if we are to interpret this result in the context, okay, what it's saying is basically this. Okay? If we were to assume the null hypothesis is true, okay, that the percentage of students that rarely or seldom argue with their friends is actually 0.72, our result, or one more extreme, would only happen 2.91% of the time. I'm sorry? Okay. So, if the true proportion of Yovan's students, or students at Yovan's high school who rarely or never argue with their friends, is equal to 0.72. So this would be this 0.72. That sample result that she collected, or one that's more extreme, would only occur 2.91% of the time. So now if I think about what that actually means, okay, I'm getting a result that's only happening 3% of the time. Does that seem to be a rare event? Yeah, something that's only happening 3%. Did we give you a significance level here? No, so what should we assume alpha should equal? 0.05. So that's the value I'm going to compare it to. Yep, because we weren't told what alpha was. So if we're not told, we assume 5%. Is this greater than or less than 5%? Less than 5%. So do we consider, should we be rejecting our null hypothesis here? Yes, because since it's less than 5%, okay, we're going to reject the null hypothesis. What does that actually mean? Well, it means that, hey, we actually have statistical evidence, okay, that the percentage or proportion of students at Yovan School who never or seldomly never argue with their friends is not 0.72. It's not the population proportion. We don't know if it's higher or lower. We probably suspect it's higher, because I think her result, I'd have to go back and look at how many people she interviewed and look at exactly what the sample proportion was. But we just know that at least we have statistical evidence based on her sample that it's not. We assume that the population or the national average is 0.72. So she's going to say remember, she's saying, I wonder if my school is just like the national average.
Right, and so if we are statistical, that's not.
So I would look back at my sample and say, what did my sample give me? And I might say, but I still would say it's not, since my alternative was a not equals to.
Right. As opposed to having we know that it's not as good
Or less. It could be greater than, it could be less than. My sample results suspected might have been less than or higher than, but I still don't know for sure. Right. So with the next example about the Jordanian children, that one will be because of the lessons. We will actually, if we reject it. Right, what I'm saying is if we reject the null hypothesis on that one, the alternative is less than. We can actually say less than.
as opposed to just saying it's not.
Right. Yeah. All right, let's take a look at the second one here real quick. In the previous example, number 2, it says for a study of Jordanian children, the sample mean of hemoglobin level was 11.3 grams per deciliter, and the sample standard deviation was 1.6 grams per deciliter. A significance test yielded a p-value of 0.0016. So what it's saying here is this. We made the assumption that the mean was 12. We got a result of 11.3. We were doing a less than test, so I'm only concentrating on the lower side. Here's my p-value. This p-value is 0.0016. Okay? So if I'm interpreting what that value means, okay? If the true mean is actually 12, okay, then there's a 0.16% chance of getting a result of 11.3 grams per deciliter or less. Again, we always need to state, hey, if the null hypothesis is true, this is the probability of my result actually happening. Bless you. So based on that p-value, are we going to reject the null hypothesis? Is it less than, here it says, what conclusions would you make if the significance level was 5% or even 1%? What would you be doing? You would what? You would reject. This 0.16% is less than both of these values. So in both cases, we're going to reject the null hypothesis. Okay? So we would actually conclude that the mean hemoglobin level for Jordanian children is less than 12 grams per deciliter. If it's less than 12, that's going to suggest, okay, that they may be in risk of anemia. Notice how I'm saying they may be in risk. I'm not saying they are in risk. I'm just saying they might be. That's what the statistics is at least showing.